In the previous lesson, we connected three balanced phasors to a YY circuit and discovered that the line voltage equals square root of 3 times the phase voltage. Now we flip the topology to delta. Three impedances form a closed triangle. There is no neutral. The square root of 3 factor reappears, but this time on the current side. Here is the standard delta connection. Three impedances Z delta sit between the three line terminals A, B, and C, forming a closed triangle. Notice what is missing. There is no neutral point and no fourth wire. Each impedance carries a phase current, and each line carries a line current. The fundamental difference from Y is that in delta, the phase voltage equals the line voltage. The same VAB that drives the line in Y now drives one entire impedance arm of the delta. In delta, the three phase currents flow inside the triangle. IAB flows from A to B through the first impedance, IBC from B to C, and ICA from C to A. For a balanced positive sequence load, these three currents form their own balanced set, equal in magnitude and spaced 120 degrees apart, just like the voltages were in the previous lesson. The line current IA is a current actually flowing through the wire connected to terminal A. By Kirchhoff's current law applied at node A, the current flowing in equals the currents leaving, so IA equals IAB minus ICA. Two phase currents subtract to give one line current. The same geometric question returns. What does this subtraction look like on the phasor plane? Watch the construction. IAB sits along the reference axis. ICA sits at plus 120 degrees. To form IA equals IAB minus ICA, we flip ICA to its negative, swinging it down to minus 60 degrees, and add it tip to tail to IAB. The two equal length vectors form a rhombus. The diagonal from the origin to the far corner is exactly IA. With both sides of length I phase and an internal angle of 60 degrees, the cosine rule gives a diagonal length of square root of 3 times I phase. The diagonal lands at minus 30 degrees, so IA lags IAB by 30 degrees, with magnitude root 3 I phase. Here is the symmetric headline. In delta, the line current magnitude is square root of 3 times the phase current magnitude, but it lags by 30 degrees instead of leading. The other two line currents, IB and IC, follow the same pattern, each rotated by another 120 degrees. Three line currents form a second balanced star. Same root 3 magnitude, rotated minus 30 degrees from the phase star. This is the mirror image of the YY voltage result. Now look at the voltage side in delta. Each impedance arm sits directly between two line terminals, so the voltage across one phase impedance is exactly a line-to-line voltage. In delta, V phase equals V line. There is no square root of 3 on the voltage side. Delta and Y are duals. Y puts root 3 on voltages, delta puts root 3 on currents. Now the most useful result of O. Total three-phase average power can be written in line quantities as square root of 3 times V line times I line times cosine theta, where theta is the impedance angle. This formula works for both Y and delta connections, exactly the same. Although V phase and I phase look different in Y versus delta, the line quantities VL and IL combine in such a way that the total power formula is universal. It does not depend on which connection you choose. Let us put numbers on it. Take a delta-connected load with line voltage 208 volts RMS. Each leg of the delta is Z delta equals 30 plus J15 ohms. First, the magnitude and angle of Z delta. The magnitude is square root of 1125, which is 33.54 ohms. The angle is arctangent of 15 over 30, which is 26.57 degrees. Phase current. In delta, V phase equals V line equals 208 volts. So I phase equals 208 divided by 33.54, giving 6.20 amperes RMS, lagging by 26.57 degrees. Line current. In delta, I line equals √3 times I phase, which is 1.73 2 times 6.20, giving 10.74 amperes RMS. Cosine of 26.57 degrees is 0.894. Total power. √3 times 208 times 10.74 times 0.894 equals about 3,458 watts, or 3.46 kilowatts. Compare with the YY example from the previous lesson. Same line voltage, same total power. Y or delta, the externally measurable behavior is identical when the loads are equivalent. Here is why three-phase systems matter so much. Three currents, each shifted by 120 degrees in time, flow through three coils, each placed 120 degrees apart in space. Their magnetic vectors add up to a single vector that rotates in the stator at constant speed. No mechanical motion, only electrical phase shifts produce a smoothly rotating magnetic field. This is the heart of every induction motor and every three-phase generator. 3 takeaways for delta. Line current is √3 times phase current, lagging by 30 degrees, while line voltage equals phase voltage. Total power is √3 V line, I line, cosine theta, the same universal formula whether the load is Y or delta. And the same three-phase symmetry that gave us clean equations also gives us rotating magnetic fields in machines. Next, we leave AC steady state and start the Laplace transform.